In this video, I'm going to go over Friedel-Crafts Acylation, which is another type of electrophilic aromatic substitution that is very similar to the Friedel-Crafts Alkylation that I discussed in the previous video. So in Friedel-Crafts Acylation, I still have my benzene as one of the reactants, but this time I'm reacting with an acyl chloride. I still have my aluminum trichloride as the Lewis acid catalyst. In my product, I'm going to install the acyl group onto the ring. So again, it's a substitution, right? I'm still preserving the aromaticity of the ring. But this time, rather than installing an alkyl group, I'm installing an acyl group on. Now, how does this mechanism work? So again, I'm going to start off with forming the electrophile for the reaction. So in this case, we have our acyl chloride, and I'm going to react it with aluminum trichloride. So what I'm going to get is now a carbocation on the sp2 carbon, which seems a little weird at first, right? I just said in the last video you couldn't form a carbocation on an sp2 carbon. Well, there's a couple of differences here. One is that it's next to an oxygen with a double bond, not a carbon, like in the last video, but also there's resonance stabilization here. The electrons from the oxygen can move into here, and I've got resonance now with that structure. So this helps to stabilize it as well, given I have the resonance. Obviously, it's going to favor this first of the two because the positive formal charge is on the carbon, which is less electronegative than the oxygen, but it still has a resonance structure. So that stabilizes this electrophile enough that it can act as an intermediate in this case and then be reacted with. So the reaction now, my benzene ring, I react with the electrophile, and then now, similar to last time, the chloride here deprotonates the benzene ring, the electrons return to the ring to restore aromaticity, and I get my final product and have the catalyst right back again. So that's how Friedel-Crafts acylation works.